Good afternoon, everyone. Today we will discuss the application of artificial neural network for predictive maintenance in lift installations. The presentation will cover the problem statement, our methodology, the result, and conclusions drawn. We are looking at the fatigue failure, and the fatigue failure has been a common issue in lift industry, particularly affecting key components like diverter pulleys. Traditional method, often based on calculation designed to estimate bearing life, which is part of the diverter pulley, are ill-suited to lifts. The systems are subject to varying loads, speeds, and directions, making conventional approaches inadequate for reliable predictive maintenance. The risk associated with fatigue failure is twofold. It poses safety hazard and results in economic losses through downtime and servicing costs. Therefore, managing fatigue failure is not just desirable but imperative. Our study aims to develop a robust methodology for modeling bearing fatigue life, especially in context of lift diverter pulleys. This is crucial not only for optimizing future design in terms of reliability and cost, but also proactively monitoring parts subject to cycling loads which can fail without warning. In recent years, artificial intelligence has progressively transformed the realm of predictive maintenance, especially in a sector of where reliability is a paramount importance, such as lift installation. Neural networks, as a technique of AI, simulate human brain function to identify patterns and make decisions. In our study, we especially use neural networks to detect various damages and damage states and in lift diverter pulleys. The traditional maintenance method often failed to account for variable operation conditions, thus falling short in preventing unexpected failures. Neural networks, on the other hand, allow the real-time data analysis and predictive capabilities, significantly improving both safety measurements and economic efficiency. The objective of the research is to harness this advanced technology to develop more robust and efficient predictive maintenance methodologies. Our experimental rig consists of the motor. Then there is the shaft, which is suspended or supported by two roller bearings on both sides. You can show it, so it's on both sides over here, with the accelerometer attached to one of the bearings. So this time is on the right. At the end of the shaft, there is a flywheel, which actually we use to introduce unbalanced class of the damage. The rig was especially designed to gather a diverse set of data under controlled condition, aiding in the study of various failure mechanisms. Data acquisition involved analog to digital conversion, as our accelerometer is analog, but then thanks to the BNK recorder, we actually converted into WAV form of a file. As mentioned earlier, the data first of all was collected through BNK recorder. The high-resolution analog to digital converter was used to ensure the accurate signal capture. Post-acquisition, the data was trimmed, so we've removed the beginning and the end of the movement as to eliminate the acceleration of the motor and then slowing down after the measurements. So we have consistent data set. We've defined 6 classes of damages. So the class A was undamaged state, and then B to F, where we've combined the unbalanced shaft, inner bearing ring damage, rolling element damage, compound damage, and severe bearing damage as classes. The sampling rate was actually dictated by the equipment that we have, was at 8.2 kilohertz. And the RPM of motor was set to 700 at a consistent rate, again to achieve consistent results. We employed MATLAB signal preprocessing to further pre-process the data. The raw signal underwent standardization, smoothing and centering procedure. Additionally, we added low-pass filter at cutoff at 3.5 kilohertz. You can see little spike here. This is most likely due to accelerometer constructions. So we weren't sure whether that would not affect the further analysis. Subsequently, the real coefficients of septogram was computed and utilized as features for neural network pattern recognition, NNPR in short. It's one of the MATLAB's tools which actually offers graphical user interface. And you can see here on the right hand side where it's actually comes with a pre-configured architecture. Typically it's a two-layer feed-forward network with sigmoid hidden neurons and softmax output neurons. We've applied that method. We've generated is actually matrices with various classes represented in a form. The classes were represented in the form of matrices. When NNPR2 was applied and model was run, we generated 100% accuracy of the detection in 5 of the 6 classes, with first class, which is no damage, actually getting errors in the region of 23%. So we've then in parallel deployed a generic feed-forward network. So it's the same principle as NNPR2, but we actually this because it's a generic one, we have more flexibility to actually adjust the parameter of it. So first of all we increased the numbers of layers. And then also we've added a retraining method on the same set of data. So the same data from the NNPR2 was taken to the generic feed-forward network. We've achieved, first of all, 35% of misclassification, again for the class 1 or class A, which is the no damage one. Then post-retraining, we lower it down to 30%. So in both cases, we have misclassification of the no damage state. We've then restarted and we took a different approach. First of all, we've created the data store using MATLAB feature designer and a classification learner. We were able to actually further analyze the data. So first of all, original data was pre-processed as previously. Then split into 1 second intervals or 1 second bits, which were actually saved into separate files. Each second was representing 11.6 rotations of the shaft, so that was sufficient for us to actually work with this data. We then employed automated feature extraction using the feature, if I present here, so this is the feature extraction, and this is the automated part of the feature extraction. So we can actually choose whether we want a time domain or frequency domain for the features to be extracted from the data set that we provide. As a result, we got a set of features, and also they were analyzed in their performance using the analysis of variance. And from this data, we concluded that 10 of the features were worthy of taking it further for the analysis. Consequently, we've used this, we exported the features into the classification learner app. So you can see it down here, and this is actually the features that we extracted and moved over to the classification learner app. As well, it's worth mentioning that we secured 20% of data as a testing data. So this is data that was not used for training, was only for testing. So we can actually check that it's not, with the new data, we're still getting good results. Once the classification learner was run, we basically employed, so the way it works, we train various models of neural networks, and this way, because they are all set in here, we can actually compare the results and see what's the efficiency, what's the prediction of various methods for the training and also in testing. As a result, we found 4 models that gave us 100% accuracy for those 6 classes. So they were like a linear discriminant, the efficient logistic regression, and 2 others. So these all gave us 100% accuracy. So we looked at it, gathered information from what we've done so far. First of all, we had to take into consideration that this was all done in laboratory conditions, and also with the rig that we devised and was fully tested. It was perfect conditions. So we'd have to take into account the real data in the future. So we'd have to analyze the real data taken from the lift and failure, and also we were looking into MATLAB's, again, MATLAB's predictive maintenance toolbox. So MATLAB actually developed a toolbox which helps with the prediction of the failure. There are 3 methods for that, 3 models. So we've got survival, degradation, and similarity models. Depending on what data we have, we can actually apply one of those 3. So you can see the survival model. We only have the time to failure. We don't have any data across the lifespan of the component. Degradation, we have all the information leading to the certain point, the threshold. That was basically this is the place where the parts were changed. They were not allowed to fail, but we have all the data to actually classify that. And then the similarity model, when you have all the data collected from the moment of installation to the final failure of the method. Using the same principle as we did so far with training the model, and then using that data to actually predict the remaining useful life. We can apply one of those 3 models and have information how long, based on the state of current component, how much of a lifetime, how long of a lifetime there is. In summary, our research validates the use of artificial neural networks in detecting and predicting damage in key lift components. The model accuracy frequently exceeded 80%, with some cases reaching 100% accuracy with recognizing the classes. The study has substantial implication for lift industry, promoting shift towards proactive AI-driven maintenance strategies. Future work will focus on integrating the model with MATLAB predictive maintenance toolbox, as I shown before, and gathering more diverse data for real-world applications, so we can actually see how it performs in real life. In conclusion, this research suggests a promising future for a safer and more reliable lift system. Thank you.